Sure.
What do you think? So, the first person who will congratulate us with our conference is Professor von Renessy. Please.
Yes, dear Andrei Anatolovich, it's a great honor and a pleasure that we do this seminar. It's a slightly, or this conference, it's a slightly extended version of the seminar that we had, was it last year or the year before? That was already a very fruitful and nice meeting, and it gave me very good inspiration and everybody else. And it's a great pleasure that we do this again. And I hope that there will be not so long time in the future when we can do such a conference in person. So I'm happy that everybody can attend, and I'm looking forward to all these talks. And I'm very grateful for the collaboration that we have, Andrei, with the two institutes in Kyiv and Leipzig. And I think the talks that we see during the conference, to some extent, also reflect this good cooperation.
Okay. Thank you very much. And let me continue with the opening ceremony. I want to say that I also hope that this conference became to be a traditional conference and will be hold a lot of years in the future. But in this year, we decided to move it from the June to September due to the interesting occasion. We have now 95th birthday of Anatoly Vladimirovich Skorokhod. It is not a big jubilee, so we decided not to organize large international world international conference, but we decided to devote our meetings to this person and to make some characterization of our meetings. I want to show you some very small idea of Skorokhod. Let me demonstrate my screen. Here is my screen. Hope it is visible now. And here is a small presentation which I prepared. You know, Anatoly Vladimirovich Skorokhod was a person who never wrote a paper or say something on or deliver a talk at the seminar beginning with the words. Now I just generalize something, or I do something as it was done before, but I just do something small. He always tried to create new ideas. And it happened that his ideas lives for years. Sometime the initial idea of Skorokhod did not attract a lot of attention of mathematicians, but after years it blew up, and mathematicians began to use it, and somebody say, "Oh, I remember the paper of Skorokhod." So let me say you a few words about his idea of generalization of stochastic integral. Initially, his paper appears in 1975, and the idea was very simple. For a random function xt, which is measured with respect to sigma field generated by the Wiener process, we all know there is Ito-Wiener expansion. Like xt is equal to series of multiple Ito-Wiener integral with deterministic kernels. Sometimes it is useful to write this series not as integral with respect to simplicities, but integral with respect to cube, with the usual formal agreement that we have symmetric kernel. If we do this, then we take this an with tilde symmetric, and we have a very good representation like Parseval formula for expectation of xt square. It is well known now. What was the idea of Skorokhod? You see here additional variable t because x is random function. So he proposed, let's do symmetrization with respect to all variables. And then organize new series. And this series is the series which contain multiple integrals with symmetrized kernels. And it occurs that a very interesting fact holds, namely, if x is adapted function, we get the well-known Ito integral. So this algebraic, very simple procedure gives us Ito integral. From this point of view, Skorokhod called this operator by extended stochastic integral, and he formulated this definition in abstract case because he preferred to formulate things in general setup. So he proposed to use general Hilbert space instead of L201. He proposed to use white noise psi, Gaussian white noise psi in Hilbert space instead of W dot. And then he introduced conjugated operator, which is called by stochastic derivative. Several years after, it looks like this paper is very abstract, and it did not attract attention of other people. But after this, people realized that this Skorokhod stochastic derivative is nothing else than Malevin derivative, and that Malevin calculus actually is very related to Skorokhod construction of extended stochastic integral. After this, people who is doing quantum physics realizes that if we consider Fock space for boson for system of bosons, this Fock space is represented exactly by the kernels from the tensor powers, symmetric tensor powers of Hilbert space, symmetric because of bosons, and they have creation and annihilation operators. And this creation and annihilation operators are exactly the extended stochastic integral and stochastic derivative. So such connections were discovered, and from this point of view, this Skorokhod paper attract a lot of attention, not only of mathematicians but people who study quantum physics. And of course, it was used by different authors in construction of anticipating stochastic differential equation and so on. But this is another story. This story about straightforward way of application. But nowadays, it get new life. Because nowadays, properties of this isonormal process, now it is called by isonormal process, this is the same white noise in H, are used to characterize compact in kernel spaces in big data analysis, and I hope we will see such talks in our mini conference. And also, one can see that properties of generalized Gaussian random elements, by the way, they also were introduced by Skorokhod in his book, which was published in the same year, Random Linear Operators, are used now in Gaussian free field theory, which is developed when we do scaling of Eisen models, spin glass models, and so on. So by this short representation, I just wanted to illustrate how one idea of Skorokhod get a new life and get a very long life, like 50 years. From this point of view, I hope that the new ideas which we will see during our mini conference also will have a long life and will be the talk will be fruitful and useful for all participants. I wish everybody success in this conference. Thank you.
Thank you.
And now Nasir Ghani from Tashkent also will congratulate us.
Okay. Good afternoon. Really, I'm congratulating all scientists from Ukraine because not in all involved. So today is a very important date. And it is a great honor for me to participate in this conference, and even greater privilege to be among of organizers, and a special distinction to take part in the opening ceremony. During my PhD studies, I worked on certain aspects of ergodic theory and required detailed information on the description of sequences of singular measures. I found precisely what I needed in Anatoly Vladimovich books, Theory of Stochastic Processes, first volume, chapter 8. And holding this book for the first time, I was deeply impressed by the richness of the material, the abundance of significant results, and above all, the way in which it revealed the profound interconnections among virtually all branches in mathematics. I was and remain greatly inspired by the other remarkable encyclopedic knowledge. I also had the privilege of seeing and listening to Anatoly Vladimirovich in person in 1960 during the first International Bernoulli Society Congress, which was held in Tashkent. I convinced that the works of Anatoly Vladimirovich will continue to be of great value for as long as mathematical essay endures, and his name will be remembered with honor as that of a scholar who made an invaluable contribution to the foundation of and development of the theory of stochastic process. That is all for me. Thank you.
Okay. Thank you very much. And I think that now we have a time to ask Andrei Pilipenko to be head of the first session. Please, Andrei.
Okay. Thank you, Andrei Anatolievich. So let us start the first session. And the first speaker is Nasir Ganikadjaev. So please continue. And the talk is a limit theorem for triangular arrays generated by Potts model.
Thank you, Mr. Chairman. So, okay. So now, again, problems. Where are documents? So suddenly I cannot find my presentation. So I don't know. Microphone. 1 minute. Georgi, please help me.
Okay, so I share the screen, yes?
Yeah.
Okay.
So this is my problem sometimes. Okay, this is the title, and here I would like to discuss some connection between model of statistical physics like Potts model and connection between branching processes. That is some problem of this stochastic mechanics. One can be reduced to well-known results of branching processes. So next please. So the main goal of this presentation to demonstrate that the limit theorems for limit gives measures of this model with 2m plus 1 spins on the Kelly tree of order also 2m plus 1. One can consider as example of multi-type branching processes. So now in a little bit. So now let F, this is the set of spins from minus m, denoted like minus m till m, here exactly 2m plus 1 spins with a set of spin values. And we consider also semi-infinite Kelly tree of such the same order, 2m plus 1. That is infinite graph without cycles with 2m plus 2 edges issuing from each vertex except for root x0, which has only 2m plus 1. So here V is the set of vertices and E is the set of edges. Next, please. As example, this is Kelly tree of second order, x0 root. So this from this one issue 2 edges, this one 3, 2 up and 1 down, and this is go up, so go to infinity. So this example, so we can consider tree of any order. So okay, next please. So now the same particles of this vertices of this tree we can consider as particle we can consider as a point of the tree. This tree, then each particle produce exactly 2m plus 1 particles. Assume that given a particle which is one of the 2m plus 1 types, if it is either type, it can produce for the next generation particles of all 2m plus 1 types. Georgi, please come back to previous picture. Previous slide, please. Georgi. Previous slide. No. Oh, this one. So, for example, this is particle produce exactly these 2 particles. This one later will produce exactly these 2, and so on. Okay, thank you. Go back. Next. So now we can, sorry, previous one. So if PAK, this is probability that particles of type AK produce so much particles of type A minus M, so much particles of type M minus plus 1, and so on, and IM these particles of type AM, then the sum of all IKs should be exactly equal to M plus 1. This is, of course, our some restriction to branching process, because usually considered so the number branching particles may be infinity many. So now the behavior of this process depends on the expected number of each type of particles. This expectation is computed like this one. So next one. So now we consider this matrix. This is all possible expectations. This is matrix of size to keep to m plus 1 by 2m plus 1. So now let xn will be this vector, random vector, where x and ak is the number of particles of type ak after n generation. Then, according Harris theorem, there is unique probability vector W such that this eigenvalues M. And the basic limit theorem for branch processes states that so this ratio converges with probability 1 limiting vector. And this theorem requires some additional condition on the distribution of the number of particles produced by single particles. For example, it is sufficient to assume that the variance of this distribution be finite. Proof of this theorem we can find in various books. Okay, next. So later, Kesten, this other Stigium, proved additional limit theorem for multi-type branching processes. If assumed so that n this value, xn multiplied by a, where a is vector orthogonal previous w, let r is the second largest eigenvalues by modulo, then it's proven that if square absolute value of square of this second eigenvalue less than largest eigenvalue m, so this ratio converge in distribution to normal random variables. So now our main goal to consider support model and describe Markov measure, and for this measure verify Kesten-Stigium's conditions. Okay, next, please. So this is semi-infinite Cayley tree. So Wn, this is so the distance is the number of edges connecting to vertices. So Wn, this is sphere, and this is ball of radius n. So now this is an important notion. Omega, this is the set of all configurations. That is a function which one defined as at any x, wx, this is some spin. So now we can define a family of random variables defined on the same space like this one. This is well-known coordinate function. Then this family's function, sigma x, so one can consider as a triangular array scheme of and use some idea of scheme series. So this is field. This is not process. This is fields because on Cayley tree we don't have order. And then we can consider this random variable xn as sum of all sigma x on the sphere or radius n. So this is random variables which we will consider later. Okay, thank you. Next. Okay, next one. So now, for brevity, I will consider case when m equal 1. And respectively, we consider only 3 spins, -1, 0, and +1. So, and sigma omega, this is the set of all configurations. Okay, next one. So now our main goal to specify some measure. So on this space of all configurations. And for the one we will use, consider Hamiltonian of Potts model. Hamiltonian was this usually specified like this one. This is J, this is some constant, maybe positive, negative, but we will consider case J positive. So Of course, this is sum is series, so we cannot operate with this series. So here you use whole idea. We will consider on finite subset Vn, this sigma n, the set of all configurations. So this set is finite. So now we will fix some boundary configuration on complement of Vn. And so we can consider different type of boundary configurations. And fixing some boundary configurations, we can consider conditional Hamiltonian, conditional energy, like this one. This is sum of when all x and y in Vn, and second sum when one x belong Vn and y does not belong Vn. Then automatically y will belong to W n plus 1. So this is now finite sum. So this for finite case, we can introduce conditional Gibbs measure. Next, please. So this standard way how we define a conditional Gibbs measure. Here important coefficients beta. Beta, this is inverse temperature, that is beta equal to 1 over T. So when temperature very high, beta go to 0. In this case, we have simple case. When temperature low, then beta will increase, and this can arise interesting situations.
Excuse
Now
me,
we have,
excuse me,
yes.
Nasir, can I ask you, why do you need beta and J? What is the difference now between beta, parameter beta, and parameter J, which you already input into Hamiltonian?
No, this is J, this is parameter of our Hamiltonian. This G is this measure this interaction between two neighbors. Course
But
of interaction.
you have, if you write sum, it will be multiplied, beta on J.
No. Beta is separate. This is temperature 1 over P.
Yes,
T temperature.
I understand, but it is now. Georgi, can you please show us definition of the Hamiltonian? No, definition. Previous slide.
Yeah. Okay.
Here,
So of
you
course you
see,
can put here. We can consider family of
here
beta.
is conditional Hamiltonian.
Yeah.
And now you multiply it on beta. So you
Yeah.
have only
But
product.
this
Beta and
beta.
J.
Okay, we are considering thermodynamic limit. That is a connection between how to change it with changing temperature. But the reason this is, of course, here formally I can put here beta, but this is formally only because we will consider below find critical beta for which we have assume central
So
limit
you
theorem.
want to distinguish some intrinsic properties of Hamiltonian and temperature.
Yeah. So
And
this
what is the delta?
delta
It is,
Kronecker symbol.
Mhm.
This is if Kronecker symbol.
if they are neighbors, it is equal to 1.
Yeah. Yes, correct.
Okay, thank you.
Come back, please. Okay. So we can define the sequence of conditional Gibbs measure. And so now one can prove so when exists the limit. If a limit exists, this one is called limit Gibbs measure. And existing of limit, of course, depend from choice of boundary configuration. If for different configurations, maybe for different boundary configuration, maybe the limit does not exist, or maybe different limits. So this one is interesting. So it depends from boundary configuration. Okay, next. So we will show some calculations. So maybe this one I can omit because I have no time now. Okay, so now I will produce some recurrent equations and prove existing of limit. Okay, next, please. So this is notation, ratio, this ratio. So we can produce such a recurrent equation. And so here what parameter theta. This is expectation power e power exponent beta j. So they are different. So beta different, j different. Okay, next. So we have this dynamical system and investigate existence of limit of fixed points. For this one, we have to solve the system of equations. And solving next one, solving these equations, we have if u equal t, v previous one. I have such equations. And v equal 1 also is easy to check. So v equal 1 is solution previous equation. For example, put here in 1, 6, you can put v equal 1, we will have equality. And u equal 1, that is maybe 3 cases, u equal v equal 1, and u equal 1. Okay, next. So such way we have 7 solutions, and we can consider 7 different limit Gibbs measures. So simplest of them when the first case, when q equal 1 and v equal 1. Okay, why? Okay, next slide. So now this is okay, this calculation to show. So there is so 3 solution for okay, next one. Next. Okay, next. Okay, so for solutions, we can compute, specify measures of one-dimensional cylinder sets like this one. For one measure generated by first solution. This is second measure generated by third solution. And this is measure which one is generated by solution which one equal to 1. And in this case, we have uniform distribution. That is a simple situation. Okay, next. So now we can compute measures of 4-dimensional cylinder set. That is root and 3 vertices above on W1. And compute these ratios, these simple things. Okay, next. Next, Gabriel. Next. So I can now define transition matrix. This is transition from spin -1 to this itself, from -1 to 0, and from -1 to +1, and so on. And so now we can compute this transition probabilities using previous calculations. So next. So this is a ratio. I can compute some ratios. And next, so we have so very interesting, very simple matrix, double stochastic matrix. So, and we will operate with this matrix. Next. So, okay, this one, the next one. Okay. So for this case, we will compute for three particles this expectations like this one. And okay, next. Okay, next. So next and next. So Georgi, next one. So okay, now I am computing here expectations for this case. So substituting, we have this equality 3 times previous transition probability. And all other cases we can compute like this one. And we will have next such matrix M, which one is 3 times. This is double stochastic matrix. Very simple. So now for this matrix, we have largest eigenvalue 3. Second one, insert eigenvalues, this is this ratio. So now the largest eigenvalue for lambda with eigenvector and the V vector has such form. So using now branching theorem, the branching theorem, previous one state that this random vector converge to vector in the direction this W. So, and since we have this here 3 power n, this is number of all vertices in Vn. So this ratio equal to 1. So here, next one. So now, so this one proves that for Markov measure, proportion of plus spins on Wn approaches the component W plus of the fixed vector W. So in this case, we have this ratio converge. Then this one also converge, also will converge. So now we assume as above that n this magnetization. So now it is true of the following statement. Next slide, please. So this is our main theorem. So this if theta, this is was exponent beta g less than this ratio, then magnetization means expectation over this one converges in distribution to a normal law. So in our case, this expectation also will be 0. So since now proof follow through Keston theorem, lambda 2 already computed equal to this value, the second largest eigenvalue. Then its square will be less than 3, largest eigenvalue, if theta greater than this ratio. And using limit theorem of Keston-Stigum, we have this is so the ratio converge in distribution to normal law. In this case, we can compute critical temperature. This is critical temperature, and for all temperature greater than this critical temperature, we have the central limit theorem. Okay, now I should note, so I can here consider simple case when we have very simple solution when distribution is uniform, and we have very simple Markov stochastic matrix like B stochastic. But if I will try to consider other measures, in this case, situation very rather difficult because First of all, other roots has some. We have to solve cubic equations, and solution has some form a little bit complete, and operate with the solution and compute matrix M and investigate its eigenvalues. So necessary may be long time and difficult, huge work. So here I consider only a simple case, and my result was so for this theta when parameter less than this one, we have first of all Keston theorem has a few other means. So for example, in this case, this corresponding measure will be non-decomposable. This is okay. So неразложимая мера. Okay, Russian. I think that is all. So I try to show connection between two rather far fields, statistical mechanics and branching processes. So here we have unexpected relation connection. Okay, that is all from me. Thank you.
Thank you very much for interesting talk. We have 3 minutes for questions. So are there any questions or comments?
Yes,
Yes,
can you
please.
comment? Yeah, Max is here. So interesting, very interesting presentation. Thank you very much. Can you comment a little bit on the role of this critical temperature? Can you give some physical explanation to this, or is it just for you a mathematical?
Yes, there are physical motivation. So we usually below for well-known models, when we consider other measures, when we for temperature, low temperature less than critical, there exists at least two different limit measures. That is, for at least for two different boundary configuration, we can reach different measure.
Sure.
This
Sure.
one usually is called phase transition.
Yes.
But
yes,
for high temperature, when temperature larger than critical temperature, we don't have this phenomena, phase transition. In this
But
case, we have single measure.
but the question was a little bit more specific regarding that, how this connection to this branching process, how this gives additional insight into the precise value of the critical temperature. So can you use the branching process to say something about the statistical mechanics model, but does it also produce some additional physical interpretation for the...
No, here we have for temperature less than critical, we have central limit theorem. Higher does not have something like this one. So there is some different direction. Yeah.
Any other maybe short question?
I also have a question, the following. You just say that among the points on which you have on the nth level, the number of plus and minus is such that it appropriately normalizing satisfies central limit theorem. But what you can say about the distribution of signs between, for example, minuses between pluses? Is it uniform or something? I think that it must be uniform because the parts of the tree looks like the initial tree. But is it true or not?
No, this depends of considered limit Gibbs measure.
Mm-hmm.
So here I consider simple case. In this case of yes, it's true. But if already I not, if I will consider another measure, when, for example, probability of plus one spin differs than probability of minus one spins. So in this case, we will have some problems. So I consider here simple case when all spins, all one-dimensional cylinder sets have the same measure, the same Gibbs measure, so 1/3.
Okay.
So, simple
Thank you.
case. Okay. Thank you very much for your attention.
Thank you, Nasir. And we have to continue. And the next speaker is Alexander Weiss with a talk on strong failure regularization of 1D nonlinear transport by reflected Ornstein-Uhlenbeck noise. Okay, please.
Hello, can you see my screen?
Yes, we do.
Okay.
Alexander, you... yes.
Hello? Yes?
Yeah.
Can you hear me?
Yes, we hear, and now it's better.
Okay. So, thank you very much for the introduction. Yeah, as it was just said, my topic is strong failure regularization of a 1D nonlinear transport equation, and I will present joint work with my supervisor Max von Renesse. And let us quickly begin. So I will start with consideration, or well, with explaining a little bit about the torus, because our considerations are actually made on the one-dimensional torus. This is where the 1D comes from. It's not from, yeah, well, not the Euclidean plane. Sorry, let me just move my camera a little bit. And then I will explain the mathematical model that we were considering, and in the end, the main result, which is the strong failure regularization. But before we start, let me quickly introduce this regularization by noise topic with a very, well, silly example, but it should illustrate what I want to show later. So let's consider such an ODE here, which is just, a constant ODE, so very silly ODE. And if we look at the semi-group, which is induced by this ODE, then it's just, well, PT of f is just equal to any function f. And this is obviously not a strong failure group because PT of f is not continuous whenever f is not continuous. But by adding noise, we regularize the semi-group in the following way. So, we just add the noise, and then the induced semi-group, which is the well-known heat semi-group, is also well known to be regularizing. So if whenever we input a discontinuous f, the semi-group will be continuous. Well, it will even be smooth in this case, but what we only want to consider is continuity, so the strong failure property. Okay, so and then before we actually begin, let me quickly introduce ODEs on the torus. So the torus in itself is a Riemannian manifold, but one can easily consider ordinary differential equations on the torus without knowing a lot about manifolds or anything actually. We will represent the torus by the quotient space R to Z. And let us consider the following ODE on R, where B is Lipschitz and bounded for simplicity and a one periodic function. Then this ODE is well known by, well known to be well posed. And due to the periodicity of B, sorry, this is a typo, there should be a B, one can deduce that the following property here holds, which is the so-called equivariance of the solution. So by this property here, one can show that the solution can be identified as a process or, well, as a map on the torus, as a continuous map on the torus. Right, so since the torus is a periodic space in a sense, we want to identify all notions on the torus with its periodic counterparts on R. Let us first begin with the Wasserstein space, which is the space of periodic measures, mu, just probability measures. And we identify them with periodic measures like this. So they should have mass 1 on each segment of length 1. And they should have this periodicity property. So whenever we shift the set, then the value of the set under mu should be the same. And we will equip the space with the Wasserstein distance. So gamma 2 squared here is just the Wasserstein distance with the induced distance on the torus. Okay, then let me quickly also define the function spaces on the torus, which are basically the periodic counterparts which we know from R. So whenever we consider some function space on the torus, it is just the functions from R to R such that they suffice periodicity and they have the property, well, on R. In the case of L2, for example, they should be square integrable on length 1, on a interval of length 1, and one periodic almost everywhere. And for continuous functions, continuously differentiable functions, the functions should be continuously differentiable on R, and also one periodic. And then, yeah, the induced norms are just on the segments from 0 to 1. Lambda here is the Lebesgue measure. Okay, and now that we have very briefly introduced a little bit of calculus on the torus, I want to introduce the model that we were following. So we were investigating the following equations with interaction on the torus, but not actually the equations with interaction, but the induced measure-valued process. Well, they are well known, and I guess here in this audience, since they were introduced by Andrei Dorogovtsev. And to consider this equation on the torus, we assume that the coefficient b here is one periodic whenever we fix, for every fixed measure mu. And b should also be Lipschitz and bounded with respect to both variables. Then this equation will be well posed. And moreover, this equation is the Lagrangian form of a transport equation. Namely, this measure mu induces a nonlinear transport equation, which is our main object that we want to regularize in this talk. So we want to add terms to this equation here in order to get a strong Feller semigroup. And since the analysis on the Wasserstein space is complicated and we are actually only on the one-dimensional torus, we will exploit a property such that the Wasserstein space is actually identifiable with a space of functions, namely the inverse cumulative distribution functions, because, well, as we all know from, I guess, our first or second course of probability theory, probability measures can always be identified with inverse cumulative distribution functions by just, because every distribution can be recovered by applying the inverse cumulative distribution function on a uniform distribution. This is actually, how you can generate every distribution that you want. But in one dimension, we also have a very good property because the two space of these functions, or the functions which have finite, so the Wasserstein space, the Wasserstein 2 space of probability measures is actually isometric to these inverse cumulative distribution functions via the L2 norm or L2 distance in case of the torus. And let me quickly show a result with this. So we will consider the space G1, which will be the functions from R to R, which are right continuous and increasing. And in the case of the torus, they also must suffice this condition here, which is equivariance condition. These functions are exactly the inverse cumulative distribution functions. So by this, one can generate a probability measure. And then this lemma here in the work of von Renesse and Karl Theodor Sturm says that the space G1 is isometric and bijective to the Wasserstein space with the following map. Here, the inverse cumulative distribution function G mu, or just a function from the space G1, is actually mapped to the push forward of the push forward of the Lebesgue measure, which then creates this measure mu, as we have all learned in our first course or second course of probability theory. And moreover, this distance here, which is defined like this and very much looks like a L2 distance, but with this additional rotation term, translation term, which is added because the Lebesgue measure on the torus is translation invariant, and we build the infimum over all such possible translations. And the result is that this L2 norm, or sort of L2 distance, is the L2 Wasserstein distance on the torus. And we will use this property and transport our measure-valued transport equation to a evolution equation on the space of these functions. Okay, but first of all, we actually need to derive an evolution equation for these functions. So let's denote, let the inverse cumulative distribution functions be denoted by f mu t for each mu t, and f mu the inverse CDF to mu. Then we get the following. Sorry, there is a typo here, but we don't have mu naught, but mu. But mu t is by definition, as we have seen a couple of slides before, it's just a push forward of our initial measure and the flow generated from this ODE. But then we can rewrite this measure mu by the Lebesgue measure and the inverse CDF push forwarded with respect to it. And then we can rewrite this term over here to, the concatenation of the flow and the inverse CDF inserted into the flow. Then from this we can see that actually f mu t must solve the exact same equation as the equation with interaction, but we don't start in the identity function, but we start, we perturb the equation by this initial inverse CDF and thus start in the inverse CDF here, f mu. Okay, now we want to regularize this equation, so we want to add some noise, but this is not very easy because if we really want to have a meaningful addition of noise, we must guarantee somehow that this function here stays increasing, because this is, this is an important property of the space over here. We want to stay in the space. So this is not very easy, and there has been an Ansatz made by De La Rue to construct a reflection which actually forces these equations to stay increasing. But the results they get are, although in the correct topology, they only get a weak Feller result. So weak Feller is sometimes also just the normal Feller property, which tells me that if I apply continuous function, well, if I apply my semigroup to a continuous function, then the semigroup stays continuous. Instead of this, we will do something different because it is, yeah, well, we can actually prove there is strong Feller property, but we will later see that it will be in the wrong topology, not in the Wasserstein topology, but in a stronger one. So in order to get there, let us differentiate this equation here with respect to the spatial variable, obviously assuming that everything is differentiable and the derivatives are good. So let's, for simplicity, assume pure smoothness of everything. After differentiating, we get this equation here for the derivative gt mu. And we very quickly see that the problem from keeping this equation up here increasing reduces to keeping this here positive, which is a lot easier to do because there is very well-known theory on reflected equations. As you may well know, so since this is a Skorokhod conference, in the finite dimensional case, it's actually called Skorokhod problem. And we would rather focus on this and, well, try this approach. But first of all, we need to rewrite this equation into a closed form. So as we see, we have here an ft mu and a mu t, which is not really connected to gt mu. And therefore, we want to, well, we need something to recover our function from its derivative. And one can do it in this easy way here. So let f be a function and g be its derivative. Then we can write the difference of f of u minus f of v just by the integral of g. And then by integrating with respect to v and the Lebesgue measure, we get that f of u is actually just this integral here plus the mean of the function. Okay, and we will use this, well, to write the equation into a closed form. So denote this antiderivative operator like this. We will call it A for antiderivative for a one periodic function. And then we can rewrite the equation just by inserting, instead of ft mu, just our antiderivative operator. And we actually get a closed form of the equation. But we need to get a second equation for the mean because, well, yeah, just the derivative is not enough to recover the function from it. So we have this, yeah, well, this is an infinite dimensional, but let's say two-dimensional equation in quotation marks. Okay, and this is an equation that we now want to regularize and show the by adding noise and by adding a reflection term in order to get a strong Feller property. And this will be done in the following way. So one problem is that we need to insert a Laplace operator because yeah, evolution equations of first order evolution equations are not very well regularizing, but second order equations are, and therefore, well, this Laplace operator will make everything very good. Here in the middle, we have our term from before, and we additionally add noise here and a reflection term here to keep the equation positive. And well, the one-dimensional process we just simply we just simply add noise here with a one-dimensional Brownian motion. And here we add space-time white noise on the space L2T. Now, since we are on the torus, we also we have to prescribe boundary conditions, and on the torus this would be periodic boundary conditions. We wanted to stay positive, which this reflection measure term should guarantee. And yeah, we want to start in a positive function, obviously. So our space-time white noise and our Brownian motions should be independent from each other, and the space-time white noise is just well, this is generalized space-time white noise, where we have independent Brownian motions summed up with the orthonormal basis of L2T, which is like just cosines and sines as we know it from our first analysis courses. Okay, so if we define such an equation, we need to define a notion for the solution. And this will be made via test functions. So first of all, a solution triple will be, a function, a one-dimensional process and a measure. And we want them to be continuous and adaptive processes, and G should be non-negative with periodic boundary conditions for all t. And for each t and for each test function phi, the equation should suffice, this equation should be sufficed almost surely. Yeah, this is just the SPDE plus we have here this reflection term. And yeah, I won't emphasize on the mean process. And a third condition that we need is that on the on this cube here, which is 0, 1 to plus r plus, the support or the integral of g with respect to this pushing up measure should be 0, which one can imagine in the following way. The measure always sleeps whenever g is positive, but as soon as g hits 0 and wants to go below 0, then eta all of a sudden wakes up and pushes it up. So the support is only located where g is 0. If you are familiar with finite dimensional, with Skorokhod problems, then this is also a very natural condition which should be part of the solution. And we impose such an equation, then we need a notion for the solution. And such reflected SPDEs have already been studied, for example, by the French Nuela and Pardoux and Donati Martin and Pardoux. And a more general result for well-posedness done by Tusheng Zhang and his PhD student. And our theorem for well-posedness is that under the conditions that B and B prime are Lipschitz and bounded, there exists a unique solution for every initial condition, where the initial condition for the function part should be a continuous function. And moreover, the solution G will be also continuous with respect to space and time, which is a very nice property of the one-dimensionality. So heat equations, stochastic heat equations in one dimensions are actual functions with good properties with respect to space. So how to solve this? One can solve this equation with a deterministic obstacle problem, where I want to quickly emphasize. So we want the solution to our deterministic obstacle problem be greater or equal than minus v, and minus v in our solution approach will be the solution to a just normal SPDE, so stochastic heat equation. And then we will, as the actual solution, consider the solution to the deterministic obstacle problem plus the SPDE. And well, the notion of solution is very similar as to what we have seen before. Then, well, the approach is for getting a solution is just a normal Picard iteration, I won't go any further on this because time is running up, but it's a Picard iteration, as I explained further earlier, at each step we solve an stochastic heat equation, and then we consider the deterministic obstacle problem with the stochastic heat equation as the obstacle. Okay, by considering all this, we can then show that for each bounded Borel function f, the following map here, where I consider Ct as a subspace of L2t, so here we actually consider, the function space of continuous functions with respect to the L2 norm, is continuous, and it can be uniquely extended to a continuous function on the entire space L2 of positive functions times R. To R. So this is not the final result, but the first step to the final result. Actually, as you have realized, we get a result with the wrong topology. So in order to clarify this, let me quickly define the space here, which is the space of measures in the Wasserstein space such that the inverse cumulative distribution function is differentiable and its derivative has a finite second moment with respect to the Lebesgue measure. And we equip the space with a metric which looks like this. Here we have the mean. So we consider the difference of the means of this inverse cumulative distributive functions plus the L2 distance of these. And this here is stronger than just the Wasserstein distance I introduced earlier. Okay, and then our main result is that after all these procedures, the Markov process, which is only defined for continuous functions in our well-positiveness result, is extendable to a Markov process on the entire space L2, and this process is Strong-Feller with state space L2. And then the family of solutions, or this induced Markov processes, induces a Markov process on the space M21T I just introduced, such that for all bounded and measurable functions f from this space to R, the following map here is continuous locally uniformly with respect to the metric here. So as a quick remark before I let questions, so to the difference of previous works, we get here a stronger result in the sense that we get a Strong-Feller result, but we have a different topology, actually a topology which we don't want to consider, which is this special topology here, but we would rather consider the Wasserstein topology. Okay, then this was my talk. Thank you for your attention. Yes.
Thank you, Alexander. We have only 1 minute or 1 or 2 minutes for questions, so please. Or comments, maybe.
May I ask a question?
Yes.
Yes, sure.
So you started with the transport equation, then you transformed it, and after that you added the noise. But of course, the interesting question would be how the noise should look like in the initial equation. Did you try to go back and write the equation in the starting form? Should it be something like in the LaRue paper via rearranged map, or maybe somehow differently defined?
So let me ask you. So you mean so we add the noise in the for the derivative?
Yes.
And then what it looks like by
Right.
transforming back. So we actually didn't look at it, but if you would do it non-rigorously, then you would integrate this here, right?
Mm-hmm.
And then you would integrate the noise, and this is not very well defined. So actually, this is not a very. It would not be a very nice object in this space here, or at this level.
Okay.
And yeah, we actually haven't really checked whether there would be connections with the reflection term in the De La Rue paper, but that is
Okay, I see.
something interesting to consider, actually. Thank
Okay,
you.
thank you.
Thank you, Alexander. And we have to continue. No, in 10 minutes. So we may ask other questions.
Okay, I have a question. On this page, exactly, you add Laplacian.
Yes.
Of course, Laplacian on the circle has different properties from Laplacian on the real line, but still it can be considered as some regularization, or do you need it just like some contraction operator?
So we needed, what do we actually need it for? So, so we need the Laplacian with periodic boundary conditions, and what we need is, we need this object here to be a function in time and space, an actual function, not a distribution or anything, but a continuous function. Because this obstacle problem here, where we insert the SPDE, the stochastic heat equation, the obstacle needs to be continuous, pointwise. And this is only possible here due to the regularizing properties in the spatial variable of the Laplacian with periodic boundary conditions.
But what do you think? Maybe this regularization property of Laplacian makes an impact on your statement. Maybe this is one of the reasons why you get strong Feller property.
Yes, definitely, definitely.
Yeah.
So this is definitely one of the main reasons. So for the evolution equation of just equations of first order, you don't really get strong Feller properties, as if I remember the literature correctly.
If I may make a comment here. So in fact, the Laplacian there, in a way, is a controlling device for the infinite dimensional noise that you add to the system. So here you want to do regularization in infinite dimensions. So you need an elliptic noise in infinite dimensions. So this is why you need to add space-time white noise, like full noise in full dimensions, means full Hilbert space-valued noise. But then you need to control the irregularity of this huge noise by adding the Laplacian to the equation to have mild solutions and kind of this kind of business. So the Laplacian here is more or less to control the wild noise, but the wild noise you need it so wild to have really noise in all dimensions in this infinite dimensional space. So this is why, if you want to work with infinite dimensional noise, you better add the Laplacian to control it.
Yes. Then you actually get a function.
To use mild solution approach effectively, if you wish.
I see. Okay. Thank you.
And what are regularity assumption on function b on the second variable?
Complete irregularity assumptions. I mean, like whatever you look at.
Sorry, on the Wasserstein.
Yes.
Just Lipschitz and just
Lipschitz.
Everything is Lipschitz and bounded. Yeah,
but after
complete
one,
regularization.
But this is not the main point. So we were. I think it's interesting, even if you have even better, more smoothness assumptions on B. The point here is like without the noise, you just have an ODE in infinite dimensions. Even if B is smooth, you cannot expect from an ODE in infinite dimensions strong Feller property.
Yes, sure.
So even if the coefficients are smooth. So that's not the main point. The question is really what kind of noise can you choose and put in this infinite dimensional situation that you stay in the space of measures and you produce strong Feller property.
And non-probability measures, yes?
No, in the probability measures. You stay in the probability measures. Right, so it's a nonlinear space, but you want to have, in a way, it's nonlinear. It's positive and stuff has this, right? So it's a convex. So you want to have this infinite dimensional noise in this nonlinear space, and still everything is nice. So that's a little bit the problem.
Okay, thank you. So other questions or comments? Okay, probably. If no, then let us thank our speaker again, and let's make a short break, like 5 minutes, until the next speaker.
Thank you.
Okay, let us continue our session, and it's my pleasure to introduce Jana Kinderknecht, who will talk about dynamical foundation of the fractional Brownian motion and related conditionally Gaussian models of anomalous diffusion. Please, Jana.
Thank you very much for the possibility to present this talk and our results. So, fractional Brownian motion. So first of all, what is the classical diffusion? We speak about classical diffusion when the mean squared displacement of the diffusing particles is proportional to time, as it is written here. And as mathematical models on the level of single particle, it is Wiener process. And on the macro level, on the level of evolution equation, it is the heat equation. And the relation between micro and macro levels are given here. That is the Wiener process, or mathematicians call it also Brownian motion, is used to represent the solution of the heat equation with initial data U0. Okay, so I call that this is the a kind of Feynman-Katz formula for the solution of this equation. We say that this process is the stochastic solution of this equation. This equation is the governing equation for this process via this connection. And so once again, this property that the mean square displacement of the diffusing particle is proportional to t, it's a kind of statistical statement. And on the level of underlying stochastic process, it is the fact that the variance of the underlying process is just t, or proportional to t. And also we know that this process is a Gaussian process, and we know that this process is a Markovian process, so there is no memory in the system. And all this structure can be generalized for a much bigger class of equations and stochastic processes. Namely, we have Markov processes, descent Markov processes, and related evolution equations. And the relation between equations and process can be proceeded via operator semigroups theory. But this is a classical theory, classical diffusion. Now, what is anomalous diffusion? Anomalous diffusion is a diffusion phenomenon when the mean square displacement of the diffusing particle is not proportional to time, and both are possible, the underlying stochastic process is no more Gaussian. So a kind of typical situation in the observations is that the mean square displacement of the observed particles is the power law of time. So with some anomalous exponent alpha, and when alpha equal to 1, then we are in the case of classical diffusion. And then when alpha is smaller than 1, we speak about subdiffusion. And when alpha is bigger than 1, we speak about superdiffusion. So it's a kind of diffusion which runs qualitatively faster or slower than the classical case. So please pay attention to this law of mean square displacements of the particles. Okay, anomalous diffusion has been observed in many different situations, both subdiffusion and superdiffusion, and we are actually interested in such type of processes occurring in biological cells. In this case, both subdiffusion and superdiffusion have been observed, and let us consider it in more details. So this is a picture, an illustration of a cell. And due to development of single particle tracking method and due to the development of physical equipment, anomalous diffusion has been observed in many different situations. So what we see in a cell, so in one hand, diffusion takes place in a crowded environment. So there are a lot of things which act as obstacles for diffusing particles. This may slow down the particle. On the other hand, these obstacles, they also move a little bit, and they kick the diffusing particle. So and there are also some transport structures in a cell, in the biological cell. So if the diffusing test particle is kicked to this transport structure, it will be transport faster than by a standard diffusion, and then we can observe super diffusion phenomena. So both sub and super diffusion seem to be reasonable in this complicated situation. So once again, classical diffusion, we have just one test particle and a water. So water is micromolecules, and a diffusing test particle is bigger. And in this situation, we have in the cell, we have a lot of sufficiently big molecules which interact with each other, kick each other in one hand. On the other hand, they are also obstacles for each other. So we should be careful with how to describe this all. Okay, so there is a kind of seminal paper of Golding and Cox, physical nature of bacterial cytoplasm. In this paper, they have just produced some experiments. They made this single particle tracking method. They applied this method for tracking fluorescently labeled mRNA molecules in some living cells of some bacteria. This is the name of the bacteria. And they have observed that the mean square displacement of this particle is a power law with alpha not 1, smaller. There are several models in the literature which describe this kind of behavior. I mean, there are different stochastic processes which have variants of this type. And one of them, so one of such processes is the so-called fractional Brownian motion. And it is a kind of usual model for anomalous diffusion. Why it is first it is a question. Nevertheless, there are different models, and there are also papers which say which investigate the data set of this paper and compare statistically with different models which can be assumed as models for this data set. And the conclusion of authors is that fractional Brownian motion seems to be a better model. So fractional Brownian motion. So I just recall that fractional Brownian motion is a centered Gaussian process that starts at 0 and has the following covariant structure. In particular, the variance looks as follows, and we see this is a power law with some exponent to h. Hurst parameter is h is between 0 and 1, so we can have sub or super diffusion if we want. If h is equal to 1/2, we are back to Wiener process and the classical situation. For h is not equal to 1/2, there is memory in the system, and our process is not a Markov process. And so, yeah, the instruments are correlated. Another nice feature of this fractional Brownian motion is that it is a self-similar process with stationary increments, and this is nice for modeling. So it's a kind of extra motivation for such type of processes as models of anomalous diffusion. Okay, but the time runs, and there are further observations made by single particle tracking methods applied for investigating processes in living cells, in biological cells. And in particular, it turned out that when we have several test particles, diffusing particles, it seems that they have their own diffusion coefficients, and this causes that the PDF is non-Gaussian anymore in the final PDF. And moreover, it seems that the Hurst exponent h, or just the exponent, the anomalous exponent in this mean square displacement of the particle, varies from realization to realization or even along a single sample path. So, so there are finer results in observations, and then there are, of course, more advanced models suggested in the literature. And some of these models are, again, based on fractional Brownian motion. So they look like this. So first step was to suggest superstatistical fractional Brownian motion, or also called randomly scaled fractional Brownian motion. It looks like this. It's a product of fractional Brownian motion with a random variable which is independent from this fractional Brownian motion, and it is positive, and it is a kind of random diffusion coefficient of a diffusing particle. This is one model which was suggested earlier, and then more recently, other models are suggested which are a kind of fractional Brownian motion with random or even time-dependent or random and time-dependent Hurst parameter. So what could this mean? Well, there are different suggestions how to interpret this, but nevertheless, there are some models which a kind of generalized fractional Brownian motion in this direction. And of course, we may combine both models, that is, we play with random diffusion coefficient and we generalize this Hurst parameter to be a random variable or a time-dependent function or a random or stochastic process. Okay, but the situation is always like this, that there are some observations, more and more advanced observations, more and more fine phenomena observed, and then physicists in the literature suggest some more advanced stochastic processes which have the properties similar to those observed. But if this process at all physical or not, this is a big question. Yeah, so it's just a suggestion that something looks like what we observe, but that's it. No more statement about how physical, how realistic these processes are. Nevertheless, let us speak a little bit more about superstatistical fractional Brownian motion. So as I said, it looks like this. And the first representative, which is the most well-known one, is the so-called generalized gray Brownian motion. It looks like this. So it's a fractional Brownian motion with Hurst parameter alpha half for this scale of alphas. And this is the random scaling. It's a square root of random variable whose Laplace transform is given in terms of Mittag-Lefler function, special function with parameter beta. Beta is in this scale. So this process is well studied in the literature. In particular, it is shown that this process is a stochastic solution of this type of evolution equation. So you see we have a Laplacian here, and then a kind of memory kernel. And if alpha is equal to beta and equal to 1, then this disappears and we are back to heat equation. If alpha is equal to beta but not equal to 1, then we have a memory kernel, which is a Riemann-Liouville fractional integral. So we are in fractional calculus. This is a time fractional heat equation. Okay. Even more in a more general situation, the processes of this type, they are stochastic solution of evolution equations of this type, where this is a pseudo-differential operator whose symbol depends on t and s, and also on the symbol of the Laplacian. That's why it is described like this. You can find the details in this paper. And in some special situations, this pseudo-differential operator may look better. Namely, it can be split into pseudo-differential operator whose symbol is a function of the symbol of the Laplacian without dependence on t and s, times a memory kernel that is times a function which depends on t and s. Such equations and operators have been discussed, and stochastic solutions of such equations have been discussed in these two papers, so you're welcome to look the details. Once again, we should be very careful in the sense that, okay, assume that this is the true evolution of what we observe on the macro level. Then we have, for example, a stochastic process which serves as a stochastic solution for this equation via this formula. But here in this formula, we use only one-dimensional marginal distribution of the process. Yes, and this is not a Markov process. So there are a lot of totally different processes which have the same one-dimensional marginal distributions, and hence lead to the same evolution. They serve as stochastic solutions of the same equation. So this raises once again the question: what is the physicality of the process we consider? Once again, in the literature, there are a lot of different processes with the same PDFs, one-dimensional marginal distributions, or with the same some properties, which are suggested as stochastic models for anomalous diffusion, just because they have the similar properties as those observed. That's it. No physicality, no more physicality in the suggested models. So this motivated our research. So we want to find a kind of dynamical foundation for the process we look at. And now I present the results of this paper together with Christian Benda, Mirko Davidio, and Gianni Pagnini. So limit theorems for the dynamical foundation of the fractional Brownian motion and related models of anomalous diffusion with random diffusion coefficient and time-dependent random Hurst parameter. So this is like the very, very recent models discussed in the physical literature. So before I present the statement of the theorem, I make a summary of what we have done. So what we consider? We consider a test particle, a single test particle surrounded by n Brownian particles. So Brownian particles are particles which are governed driven by Wiener processes. We have n Brownian particles, and the key feature is that they have different masses. We construct a system which is a system of ODEs and SDEs, such that physical principles of conservation of momentum and energy are met. And we investigate how a test particle behaves in the limit n tends to infinity, that is where the environment becomes more and more crowded. So as I said, the main ingredient is different masses. That is, we introduce an extra randomness in the system. And this source of randomness allows us to arrange this different masses of the surrounding particles. So actually, we assume that these different masses are IID random variables, independent from Brownian motions or from Wiener processes which drive our Brownian particles. So this one source of randomness allows to show that in the limit when n tends to infinity, with the use of different distributions of different masses, we obtain different processes in the limit. In particular, we are able to obtain fractional Brownian motion and also a mixture of different fractional Brownian motions with different Hertz parameters. And this means that so it's a big class of processes which are Gaussian, non-Markovian in principle, but also Wiener process is also possible in this approach, and allows variance which depends on time. That is, we allow also the changing of the character of diffusion. It may change this anomalous exponent, and it may become classical, starting from anomalous and classical, and so on and so forth. So the result is very general, but this is not all. Actually, in order to cover the latest models suggested by physicists, we actually introduced 3 sources of randomness. So this source of randomness I have already mentioned. So we describe heterogeneity of the environment by different random masses. And this leads to nonlinearity of variance in time and memory in the system. Also, we introduced the inhomogeneity of diffusing test particles. So we assume that the test particles are complex molecules, and even if we consider molecules of the same type, we are not able to create totally identical copies of the test particles. So they have a kind of individuality, even though they have the same mass. This individuality or inhomogeneity of diffusing particles is introduced as an extra source of randomness, again, independent from all Wiener processes and all below. And this will be given by a random coupling coefficient between this test particle and all other surrounding particles. And this green source of randomness will lead to non-Gaussianity of the limiting process and lead to this random diffusion coefficient, which we have seen in the model of superstatistical fractional Brownian motion. So as I said, this red, so the colors are chosen carefully. So the green one is a random scaling in homogeneity of the test particle, and this will lead to random diffusion coefficient. The red one is the source of randomness, which governs our random masses. And as I said, it leads to fractional Brownian motion in the limit, and even the case of time-dependent Hertz parameter. But if we want to add in the limit a random Hertz parameter of the limiting process, then we allow even more randomness in the environment. Namely, we introduce one more source of randomness. It will be denoted everywhere by blue, and we allow the random masses to depend on this extra random parameter, random source of randomness. So then all what is red below, it will be conditionally on this guy. And then we obtain the most general model which was considered by physicists so far. So summary, please pay attention to the colors. We have 3 sources of randomness. This is independent of Wiener processes. This is independent of Wiener processes and this guy. And these are independent of Wiener processes, this guy, but depend on the blue one. And a condition, so given this blue guy, the random masses will be IID random variables. So the motivation, physical motivation for this blue story is the following. One observes a kind of non-uniformness of heterogeneity of the environment. That is, if we have several test particles which start in different points, they behave differently, or one point behave in one way, and then after time, when it moves to another part of a cell, it behaves differently. So this is a kind of this random, extra random parameter is a kind of parameter of localization, which says in which part of the cell this diffusing particle is now situated. Okay, so extra 3 sources of randomness. So finally, what we consider. So this is the system which we consider. We consider a single test particle with position x and velocity vn, and we consider n Brownian particles with positions y and velocities u. So let us start here. So so position is the integral of velocity. We have ODE, and velocity is given by this SDE. It's a Langevin equation driven by Wiener processes. All Wiener processes are independent. So our test particle is here, and there is no SDE. It's just ODE. That is, we consider that we consider only that our particle is kicked by the surrounding Brownian particles, not by water, and we also neglect the interactions between our surrounding particles. So they are, roughly speaking, interact not with each other, but only with our test particles. So this is what is written here. So these are the coupling coefficients, and this coupling coefficient is random. It appears here. And also our surrounding particles, they have different masses. They are green, they are red, they are also random.
Yeah, excuse me, random, but IID.
I will, so next slide will give more information. So it is written here. So as I said, we are interested in the behavior when n tends to infinity. So we need to control everything, the behavior of everything in this situation. So first of all, our scaling parameters are decaying polynomially when n tends to infinity. And this does not need to be random. It's like this. And this guy is random, so there is a random variable times a polynomial decay. And this random variable is such that this random variable to the power -1 has the first moment. And this A is just the random coefficient which appear in the limit. Further, as I said, we have an extra random element, H. And given H, our masses are IID random variables with distribution, which, conditionally on H. And we control everything very carefully about the distributions, conditional distributions, in particular without going into details, some specific characteristic of this sequence of distribution of conditional distributions converge to some normal function, normal in the sense that not that bad function. And this function is very important. It's actually the variance, the conditional variance in the limiting process. So playing with distributions of masses of surrounding particles, we choose the variance of the limiting process. Okay, this is the green story gives us random diffusion coefficient, and the blue story gives us randomness in the Hurst parameter. Okay, so now we are ready to see the statement of the theorem. So theorem looks like this. We fix any t0, so we will consider the system on the interval from 0 to t0 for any t0. And under assumptions above, formulated in a rigorous way, which is not the case here, of course, and plus some technical assumptions, we consider a process of this type. So square root of A, it's this random diffusion coefficient independent from this guy. what we have here, so the G is a measurable centered Gaussian field, which is independent from A and H. And for each H, small h blue, so given H is equal to small h, this guy is a Gaussian process, yeah, with continuous paths and with this covariant structure. So you see this function V appears here, and this function V, it is any one which we can construct by playing with the random masses of the diffusing particles. So the statement is that the process Xn, so the solution of this, so the position of the test particle in the above system, converge as n tends to infinity to this nice process in distribution. Okay, half of a year ago, I presented similar result, but without random scaling and without this conditionally on H. So if just forget about blue and green story, so if we kill two sources of randomness and only play with IID random masses, then we are able to get a Gaussian process in the limit with this covariant structure. And this is already the main result, because in this way we can obtain fractional Brownian motion and many other processes. So let me give some, we have 5 minutes, let me see some examples. So this is a kind of a more precise recipe how we play with masses. So conditionally on H, we consider a reference measure, nu H, which is a Levy measure of a pure jump subordinator, any one we want. Then if we have a pure jump subordinator with a Levy measure nu H, we can consider its Laplace exponent. It looks like this. Then having this reference measure for each H, we consider the distribution of our random masses, IID random masses, conditionally on H, which is given like this. So what is here? So all these guys are absolutely continuous with respect to a given reference measure with a precise Radon-Nikodym density. So we control the support of the measures, mu n, in a very careful way. And this is a normalizing constant, which we also control in a very careful way. But nevertheless, so if we have Levy measure of a pure jump subordinator for each H, then there is a recipe how to construct the distribution of IID masses. And then the limiting variance is obtained like this. So it's actually the integral of the Laplace exponent of the reference measure. So this is the recipe. So one of the possible recipes, how to play with random masses of surrounding particles to obtain what we want. So this is the variance of the limiting Gaussian process. Okay, conditionally on H if we want. Okay, so special case. For example, if we take H to be a random variable taking values in some interval, if we take a reference measure to be a Levy measure of a stable subordinator with this index of stability, so nu looks like this, then using this recipe, the variance function in the limiting process like this, and this is a power function, so we are exactly in the case of fractional Brownian motion, conditionally on H again. So given H is equal to small h, our conditionally Gaussian process is just a fractional Brownian motion with Hurst parameter H, and hence the limiting process is something like this. So conditionally on H, so if H is equal to small h, we have just a randomly scaled fractional Brownian motion. So it's exactly a model of superstatistical fractional Brownian motion, which is discussed and investigated in the physical and mathematical literature. So having a random H, we see that in the scaling there is something which makes this factor and this factor to be dependent. So they are not independent anymore. And this also fits to experiments. So that the random scaling is dependent from this part. Okay. So there are too many different sources of randomness, yes. But if we forget about this blue story, just H is constant, then what we have here, it's a randomly scaled fractional Brownian motion. It's a nice process, which is a kind of one of standard models of anomalous diffusion. So we know how to obtain it, how to obtain its dynamical foundation. Moreover, we consider, for example, a mixture of stable pure job subordinators as reference measure. So reference measure looks like this for different HK. So we have as a source of randomness RK valued random vector. So we have this reference measure, and then the variance function in the limiting process looks like this. So it's a sum of power functions with different powers, and hence conditionally on H, so H is equal to small h. The limiting process is a sum of independent fractional Brownian motions with different Hurst parameters, and hence, so given H is equal to a fixed vector H with coordinates H1, Hk, the variance of the limiting process varies with time. So for small time, the variance is a power law governed by the smallest law, the smallest power. And for large T, the variance is like a power law with the highest degree. So it's one of examples where you see that the variance changes with time. But actually, the main formula looks like this. So it's a very broad class of processes, and we have a recipe how to obtain them, starting from a system of equations where we have actually just Wiener processes and three more sources of randomness, which impact in a needed way. Well, I guess that was everything what I wanted to. And yes, so the governing equations of these nice processes Z, as in the theorem. So this is the process Z, and the governing equations look terrible, but also they are of the type which we have already seen previously. So here we have integral differential or pseudo differential operator whose symbol depends on S, and whose symbol is a function of the symbol of the Laplace operator. So this is the explicit view of this symbol. And as a special case, we obtain what we have seen before. But I guess now it's more interesting. So the main result, yes, is this theorem. So this is the main slide of my presentation. So thank you for your attention.
Thank you, Jana, for very interesting talk.
And very fast talk.
I have one question to the organizers and to participants. Will it be possible to have slides of the presentation, maybe on the site of our institute?
Yes.
Yes, of course.
Yeah, it would be very nice.
Not only slides, but I think that most of participants already sent their abstracts too.
No.
So
abstracts is short one, but slide is.
Okay, it depends on participants. Okay. May I have a question?
Yes, please.
Jana, you said that one of the motivation is the picture of the cell where you have heavy particles, just finite number of heavy particles which are driven by different noises, in your case independent noises, and then you get desired properties of the processes. But let me ask you the following. For example, if you have just a simple picture of Wiener particles, finite number of Wiener particles in the space, it depends on the dimension of the space. We can have collision or not, and even one can try to understand how many collisions we have. In your case, what do you think? Do you have collisions between particles or not? Or it depends on the choice of the mass distribution or what?
So you see, this is a kind of toy models. It's as simple as possible. So we only consider interaction of all surrounding particles with our particle, and they well, in a sense, we looking at the structure and our assumptions, we see that all surrounding particles interact with our test particle like in the same way. And we totally neglect the interactions between surrounding particles. So I guess, well, as next steps, there are a lot of things to do, like to make the system more realistic, and to see if we still can have the same limit results. But it's a limit theorem, yeah.
But let me comment as follows. Maybe you know a book of Peter Kotelenets on stochastic differential equation, which was published in Springer, I think in 2008. And in this book, there is a long chapters, maybe two first chapters, devoted to the attempt to derive the motion of interacting Brownian particles from the physical assumptions and even physical considerations based on the size of molecules of the media, size of the large particles, speed of molecules of the media, on all these things. In physics, he involved a lot of physical things. So I think it will be useful just to check these chapters, and maybe you can improve it and bring more modern up to this, applying to these problems.
Yes, yeah. There are a lot of things to be done in the future dealing with this result. But at the moment, we are very happy to get that. So in principle, that we have Wiener processes plus extra randomness, and this in the limit gives us something non-Gaussian, non-Markov, and so on.
Okay, thank you.
Yes.
Okay, maybe one more short question.
Yeah, so
Yes,
if I
please,
may,
Max.
so somehow the setup of your model is a little bit like you have a fixed deterministic particle, so to say, which is moving in a random environment, in a changing random environment, and the whole thing has a little bit of a flavor of a homogenization analysis, so to say. Did you check the connection to corresponding homogenization results, or do you know that
No.
fractional Brownian motion is derived from the conventional homogenization system? No, you don't know, but probably it's worth checking.
But thank you for the hint. If you have some links, some references, I will be very happy to get them.
Yeah, I think it's interesting. We would be interesting to check the connection there.
Yes.
Okay,
definitely, it can be generalized. Definitely, I mean, to make the system nicer, and yeah. But still, it's already like 40 pages, so I don't know. I mean, technically, it was not that easy, and really had to be very fine with all the things.
Jana, and this equations are independent of y. You see, x depends on v depends on u,
and v, u and v,
and u depends on u and v. Why do you need y?
Just formally because we're interested in the position. Yeah, but actually the initial positions of the particles play no role, and there are assumptions on the speeds.
Okay. So actually you have interaction between speeds of molecules.
Yes.
Yes, very interesting.
Yes, but then when they kick each other, they change the impulse. Yeah, so.
Okay, we have to stop your presentation.
Yes.
I'm sorry.
Constructed by a physicist, Gianni Pagnini. So he's responsible for the physicality of the system. I have discussed with different physicists that still one can do it more physical, so to say.
I think there is a name to it. It's called active meta models. There's a new theory. Well, it means new, but this is one of the big things in physics, from my perspective. Active meta models, when you have interaction among velocities for such Hamiltonian systems.
Yes, Max, but you see here it's independent. Are molecules close or far?
Yes. So it's a toy system.
Yes, it's correct. Yes. Okay.
However, this leads to this fraction equations with fraction Laplacian. So Okay.
Yeah.
Thank you once again, Jana, for the very interesting talk. And our next speaker is Mykola Vovchansky.
I have to.
Yes, you have to stop. With a talk on operator splitting for non-homeomorphic one-dimensional stochastic flows. Please, Mykola.
Hello, everyone. It should be okay right now. Can you hear me well?
Yes.
Good. Sometimes. So I want to present some results related to the application of the Trotter-Kato formula to some non-homomorphic one-dimensional stochastic flows. It's partially joint work with Dr. Dorogovtsev. And the main object we will be dealing with is so-called how do I get rid of this? Okay. The main object we are dealing with is so-called Harris flows with drift, which are named after the person who proposed them in '84. And this is a one-dimensional system of interacting particles, such that when considered as transformation of the real line, they satisfy a semigroup property given by one. And secondly, each particle behaves as a Wiener process with drift, and those Brownian motions depend in the following way. Obviously and standardly increments are independent. We have stationarity in time. We have good convergence and continuity as given in 0.5. And those Wiener processes are related in the way that their joint covariance is given as some function phi. So if function phi is very good, we're actually going to recover pretty much standard Kunita type flows. However, a famous and standard example is Brownian web, also known as an Arati flow, in which case f of x is just an indicator of 0, which means the particles move independently and then merge without changing mass. So this model, particular model of Brownian web, appears in a lot of sources from very different point of view, including as the limit of homomorphic stochastic flows, where we have degenerate limits of the corresponding covariance functions. It also appears in works of physicists when they consider coalescing and annihilating systems of particles. And it's quite a universal limit object for models on lattices, including some interesting application to physical modeling of how rivers behave. And further, it was developed in works by Konorovsky and von Ronesse towards adding mass that changes when particles merge. So to summarize, we're interested, first of all, in two cases. The first case is the Arati flow with drift, when we have a purely singular interaction. And secondly, in the general Harris flow with coalescence. Because if phi and I good enough, we essentially are in the setting of standard diffeomorphic stochastic flows, which is a well known situation. From the physical point of view, if you want to think about some reasons people might be interested in Harris flow and not just Arati flow, is about the answer to this question is an attempt to generalize standard systems with correlated environmental noise in the spirit of stochastic Langevin equations that appear, for instance, in biological physics. Obviously, in most applications that are known right now, these functions that stand in front of good white noise are very good. But nevertheless, if you consider some averaging over small particles, especially in the spirit of what Kotelenets did, a natural question appears: what if we want to directly and explicitly discuss the behavior of particles that merge and not only appear as average mass? So the main idea of this talk is that we can apply the famous Lee-Trotter-Kato formula, also known as a multiplicative operator splitting, or just fractional step method, or just operator splitting in this talk, to the situation where we have a drift and singular coalescing stochastic flows by separating the drift part, which is given by OD, and the stochastic part, which is given by a purely coalescing stochastic flow. So this is a very standard result, a famous result. If we can combine two good contraction semigroups by iterating applications of such semigroups on small intervals, and when the time these compositions are defined goes to 0, we can recover the original semigroup, which is given by this generator. Now, obviously, in case where we have stochastic diffeomorphic flows, this is an already discussed topic, and here are some references that apply to this situation. And an interesting observation is that in this case, one can actually obtain a lot of results by just transferring purely mechanically results for Euler-Maruyama scheme into the setting of splitting methods. So our main results and our main interest lies in the spirit of purely coalescing flows, which are not covered by these results. So firstly, we need to formulate some assumption on drift and function phi that guarantees the existence and necessary properties of the Harris flows. So we consider symmetrical function phi and define the corresponding phi capital by demanding standard set of requirements that are directly taken from the standard definition of Harris flow. And we take drift that can be discontinuous. However, it should be regular in the terms of some function rho that has polynomial estimate of this type near the beginning and doesn't grow quicker than linear on infinity. Now, beta can effectively be negative in some cases, which allows for discontinuous drifts. And one can check that then the flow exists as defined by the series of the corresponding family of nested Martingale problems. And one can check that the limit is indeed well defined. And also, if we have some compatibility condition, then we can guarantee that the flow is purely coalescing in the sense that the image of any bounded set is a finite set for any positive time. So to compare what we have here to this case of diffeomorphic stochastic flows, we need to discuss the representation in terms of stochastical differential equations. The following result is almost from Warren and Watanabe. The reason I am putting this almost because formally we add in drift, so we need to do calculations. And though it's not hard, it's still something conditional. So if we have stochastic flows with just continuous covariance function and any bounded drift, then we can recover a proper white noise, which is defined on the reproducing kernel Hilbert space for phi in a standard way, by using a very standard construction that is shared with the case of just ordinary one-dimensional differential equations, where you can discover the field that governs the behavior of our particle by using this construction. Pretty much the same happens here. And if a square root of 1 minus phi is sufficiently good in the terms of being a member of a Holder space with sufficiently good exponent, then we have a good representation of even a coalescing and purely coalescing Harris flow as a solution, a unique strong solution of the corresponding stochastic differential equation with respect to this white noise. However, if this doesn't hold, we do not get the uniqueness. Pretty much exactly in the case of one-dimensional stochastic differential equation and Maruyama type uniqueness theorems. So as a conclusion, the case we consider is generally speaking different to the case of stochastic diffeomorphic flows because we do not have this good representation as an SD. So what is the construction we apply? We start with considering a sequence of partitions, and they define this subintervals of our interval from 0 to t. And delta n is a diameter of our partition. And we consider the semigroup generated by our ordinary differential equation. And then we can define our process un and yn by using this construction. So we use, in this situation, firstly, Harris flow with zero drift and fixed phi on a small time interval. And then we iterate with our semigroup derived from the ODE. If we have this representation of stochastic differential equation, we can write this in a very good form as just a solution of stochastic differential equations. If not, we are using this as the main definition. And again, it's very useful and easy to observe that the situation is very similar to the Euler-Maruyama scheme because it can be rewritten in the following form. It's almost a stochastic differential equation, but you have integral or your Wiener process stopped at some points in time. I will later call un a deterministic part of the splitting procedure, and yn I will call a stochastic part of a splitting procedure. And these Wiener processes depend on x, and they are related in the way was described. So before proceeding further, I just named it. We'll present what is already known in the case when we have stochastic diffeomorphic flows with no coalescence. Then we have good estimates. And pretty much exactly in the case of Euler-Maruyama scheme, we can put this supreme over T inside by losing some speed. And again, if we have the good representation of solution to stochastic differential equation with respect to some white noise, sufficiently good in the terms of Holder continuity phi, we again can just mechanically obtain what we need. Moreover, if you think about just the Euler-Maruyama scheme and a standard decomposition of the error, when we use the Euler-Maruyama approximation of the solution x, we get this representation, where this function can be written explicitly in one-dimensional, multi-dimensional cases. And again, one can easily obtain a similar representation in our operators splitting scheme, pretty much exactly the same. The main mechanical difference is that instead of going for the Ito formula, it might be beneficial to go for the stochastic Taylor expansion as wise. And we obtain pretty much the same estimate here. Now we can discuss what happens in our new case when we have a purely coalescing case. The first result is that we have finite dimensional convergence. Convergence of finite dimensional motions. And moreover, if A is not Lipschitz-Bastille satisfies sufficient compatibility conditions that guarantee the existence of the corresponding Harris flow, I can modify the splitting procedure by introducing additional regularization with respect to some small noise with some additional WT that's totally independent of our original Harris flow, and one can still obtain pretty much the same result. Even though the ODE now is not well defined. The second result concerns the convergence of the push-forward measures generated by our flows. So we consider just two types of measures. The first is just the push-forward of the Lebesgue measure under the action of the limit flow and our stochastic approximation. And we consider just general push-forward for some fixed radon measure. And then under some technical conditions, it just guarantees pretty much the existence of moments of what of measures we consider. We can obtain proper convergence in WAG and weak topology correspondingly. The method, if you want to speak about the method of the proof of this result, and can be decomposed into the tail estimates, which allows us to use the second step. And the second step is the usage of finite dimensional convergence of the corresponding flows. I assume there should exist a functional method of proving this result, but in general, how it was proved, entropy estimates and Donnelly integrals was used for control of the corresponding tails. The third part of the result concerns so-called dual or and inverse flows. So firstly, if you have just a diffeomorphic standard good Harris flow or stochastic flows in general, then you can just take direct inverse of the corresponding transformation of the real line to obtain again a Harris flow that just lives in the reverse time, and you need to do some transformation of the corresponding linear process. But if we have a purely coalescent flow, this object is still well defined, but it's discontinuous. So one way to define such inverse flows is just we take the point, the starting point, if we consider all trajectories of the original flows that go in direct time, and we take the infimum over all those particles that hit upper than x1. So all particles that hit there, and infimum of there is presented in the red line. And that leads to the following method of proving such results. So we start with ordinary splitting with some drift and some Harris flow with no drift that used. And we need to modify our splitting procedure that it now can be started at any fixed S. Instead of starting at 0, we still use the same partition. But now, if we have some K and Tnk plus 1, we can, instead of starting at this point of this subinterval, we can start exactly at this point, and on later subintervals, we just apply the standard splitting procedure. This produces functions that defined only starting for some S, and which are piecewise continuous, because splitting produces piecewise continuous functions, and we just extend them on the whole 0 T capital by putting it equal to the starting value time S. And since we use exactly one Harris flow for all these parts, we have a well-defined dual flow, because all these mappings form a coalescing flow and they are defined with the same probability space essentially. And now I will use E to denote that we have this extension procedure, and for every such finite dimensional procedure in this motion in this extended splitting procedure, we have the convergence, which is pretty much the same result. And now we can consider this product space of Skorokhod spaces, this product topology, J1 topology. And using the Kolmogorov theorem, we can define devalued d-Gaussic valued random elements by using these objects as building blocks. And instead of talking about these results, we can actually discuss the convergence of the whole random elements that live in here. And so this is a collection of all points that have some dense subset of 0t times r as they are starting in space and time points.
Cool. And this dot, it can be less than Si and greater than Si. So the flow is two directions, only one.
This is in direct time. This is in reverse time. This is dual flow. These are duals. So you start with this. Because of this formula, you can recover your dual flow by using only a countable number of points of particles inside your original flow.
But my question was, you have a dot here, and here it's like t in 0t, yes?
Yeah. So an extended S1 dot is actually a function on 0t, but on 0S1, it's just a constant.
I understand.
So it's actually constructed, but using only what happens after and starting from S1. It just avoids us to use a product space of one Skorokhod space instead of caring about this SN everywhere.
I understand.
And then we have this essentially countable collections of particles inside our flows as devalued random elements. And because of this formula that I mentioned, we can actually construct our dual flows as some mappings on this d-Gaussic. This mapping is, generally speaking, discontinuous, but it's continuous enough for us to prove this result. So we have convergence under standard compatibility conditions. We have convergence of our dual flows. So we do not. The reason I went with this construction is because, contrary to the case of diffeomorphic stochastic flows, you do not have this representation or convergence as diffusions in the terms of Kunite. But still, the whole flow is sufficiently to know just a countable collection of particles that start from everywhere dense set to discuss the whole behavior of the flow. And if we consider very briefly the case of the Brownian web, we have no representation as stochastic differential equation with respect to any noise whatsoever, contrary to the case of Harris flows where phi is continuous. And Cyrillson proved this is in general, and here in the general setting, and this is a direct proof. And the reason that those constructions that led us to discover a white noise do not converge at all in the case of Brownian web. But again, we can apply pretty much the same splitting procedure. Obviously, this is now just a piece of some Wiener process, which are independent, and we have pretty much the same result about the convergence of finite dimensional motions. However, you can also discover the speed of convergence. For that, you need iterated Wasserstein distances. So you start with standard Wasserstein distance or probability measures on R. You consider now the distribution of random push-forward measures. And you can, there are distributions which members of this iterated Wasserstein spaces. And then you have this result, which gives us a speed of convergence in terms of two logarithms. Again, first logarithm is explained directly by the method of proofs it was chosen, but the second logarithm is a more interesting question whether it's possible. The second logarithm provides an interesting question whether it's possible to get rid of it. I do not know as of now. And I want to finish my talk with a short remark about how you do coupling of coalescing stochastic differential SDE and why it's asymmetrical somewhat in terms of how the splitting procedure is applied. Because effectively, when we speak about Wasserstein distances, we speak often about coupling. It's indeed the coupling has been constructed. So if you consider just stochastic differential equation with independent Wiener processes, and you consider some splitting procedure, you can do very easily apply coalescing rules to the original stochastic differential equation, but just taking the rule that when two particles meet, the particle with a smaller number survives, and the second one merges with it. However, when you try to do this simultaneously to the splitting, you can do pretty much the same with the stochastic part. Recall that in this splitting procedure, merging, coalescing of particles can only happen on stochastic intervals because ODE is well defined and well posed, and no coalescing happens. However, so on some interval, our splitted stochastic parts can meet. However, our deterministic parts should be redefined slightly. They should live until this time, and only then they will switch. So in terms of just two processes, this deterministic part lives as the first one until this hits, as the second one until this hits, and then only it switches to the first motion. And the reason is that, as I said, it's very easy to define coalescing stochastic differential equations by just using this formula to redefine Wiener processes, but you will need another set of Wiener processes to define a corresponding splitting. So instead of just using mechanical splitting, you will need to modify the whole procedure. You will have stochastic differential equations with respect to one set of Wiener processes and splitting procedure with respect to a slightly different set of Wiener processes. And estimating the difference between these objects is actually something that leads to appearance of logarithms. So
excuse me, you have
yeah.
1 minute.
Yeah, that's exactly it. So you will need to introduce a splitting procedure with different starting points for the deterministic and stochastic part. Part discussed the relation between Wasserstein distances and distribution functions, and pretty much in the Euler-Maruyama scheme, if you know the convergence of processes, you can use exactly such results to discover convergence in terms of Wasserstein distance. That's all I wanted to tell you. Thank you.
Thank you for the interesting talk. Are there any questions or comments? Max, please, we don't hear you. Ah, no. Oh, okay.
Well,
If there are no questions, let us thank all our speakers once again and make a break until 15:30. Yes. So see you
Okay. See
in
you.
an hour.
See you. Bye.